Good afternoon. Shortly we'll hear an interesting lecture by Dr. Dimitry Yankelev on inertial sensing with atomic interferometers. This webinar is part of webinar series organized by Photonics Israel on various aspects of photonics. Photonics Israel operates within Engineering Association as a cluster of photonics entities. Our mission is to deepen the knowledge in photonics and to encourage cooperation both within Israel and with photonics entities in the world. We are holding weekly webinars on various photonics topics. We invite you to sign up to follow the activities we hold, which are published in our monthly newsletter. Per your request, the newsletter will deliver to your mail. My name is Shlomo Glaser. I am the manager of Photonics Israel. With your permission, few words in Hebrew. טכנולוגיות קוונטיות הן באמת בעלות פוטנציאל כלכלי רב, הזדמנות לתעסוקה והתפתחות אישית. אוניברסיטת בר אילן זיהתה את הנושא הזה, ובשנת הלימודים הבאה היא תפתח תוכנית שנקראת Quantum Engineering. יש לנו בקנה עוד 3 הרצאות זום בנושא הזה, בעצם עוד 2 חוץ מההרצאה הזאת, ואנחנו שוקלים לפתוח קורס למהנדסים בשם מבוא לפיזיקה וטכנולוגיות קוונטיות. באמצעות נשוב לוובינר הזה, אנחנו נשמח לשמוע את מידת העניין שלכם בקורס הזה. ישנו ספר מצוין שנקרא פיזיקה קוונטית מבוא, כתב אותו דוקטור בועז תמיר, הספר הוא בעברית, והוא באמת כתוב בשפה מאוד פשוטה, מאוד מובנת, בוודאי למהנדסים. אני מאוד ממליץ לקרוא את הספר הזה, הוא מאוד יעזור למי שירצה וירשם לקורס. עוד נושא אחד, בפברואר אנחנו עושים כנס בינלאומי בנושא של אוטומוטיב, זאת אומרת פוטוניקה בשירות מערכות נהיגה, מערכות אזהרה ומערכות ניווט ומערכות נהיגה אוטונומיות, ומי שיש לו מבין המאזינים, יש לו נושא שהוא רוצה להעלות אותו, הוא מוזמן להגיש הרצאה או פיץ'. Dr. Yankelev has worked as researcher in Rafael for the last 14 years. He earned his PhD in physics from Weizmann Institute of Science. As part of the PhD work and in collaboration with Rafael, he has specialized in quantum sensing with cold atoms interferometer. Dr. Yankelev works focusing on precise gravimetry and on developing novel techniques to improve the sensitivity and robustness of such sensors. Dr. Yankelev, the floor is yours.
Thank you, Shlomo. I will share my screen. Okay, and let's see if I can have that laser. Okay, do you see it?
Yes, we see it.
Oh, excellent. So thank you for the introduction. As Shlomo said, I work in Rafael in the Quantum Technology Center, and I recently finished my PhD in the Weizmann Institute, and essentially as part of my this joint work from both Rafael and Weizmann, as part of the PhD, me and a fellow researcher built a new lab for atom interferometers. The device itself you can see here, and this kind of devices can be used for precise and stable inertial sensing, and I will try to spend the next 45 minutes explaining exactly what, how they work and what abilities they can offer. So this is just a picture I recently found online to give some sort of partial broad overview of quantum technology, specifically on where atoms-based quantum technology platforms are headed, and you see that there are very great many possible uses and quite a lot of different applications. And what we'll be talking about today, atom interferometers can serve as for inertial sensing, which is useful obviously for navigation, and also for measuring gravity and gravity gradients, which are also very important for mineral prospecting, mapping, and more uses. In fact, most of the talk will be focused on gravimetry, sensing gravity, because this is both the most straightforward example to explain and the most mature aspect of this technology. So how does one measure gravity in general? So we can very broadly divide the gravity sensors into two kinds. First kind essentially is having a test mass and hanging it on a spring and measuring the elongation of that spring. Such devices, there are quite a few of them. They are very good in measuring short-term fluctuation. They are very sensitive. If you take the measurement you made now and the measurement you made 1 second ago, you can be quite certain that the difference between them is real. However, such devices tend to suffer from long-term drifts. If you have a physical spring, like in this, like it actually has in this device, you can imagine that this spring might experience aging, it might have a sensitivity to temperature, and so if you compare the measurement you made now to the measurement you made an hour ago, or a day ago, or a year ago, those comparisons will be quite meaningless. So this sort of measurement is called relative measurement. It generally cannot give you absolute value. The other kind of gravity sensors would be device where you take your test mass and simply drop it, let it fall, and measure how fast it is falling. This takes time. It will limit your bandwidth, it will limit your sensitivity, but it is possible to build such devices so they will be very stable. So your long-term measurements are quite meaningful, and you can compare the measurements you made right now to the measurement you made a year ago. So with atom interferometers, what I'll be talking about, we focus on absolute gravimeters. So what's the difference? So if you take this classical absolute gravimeter, inside you have your test mass, which is a freely falling mirror, and you measure it with a laser interferometer. You measure its motion relative to some stationary lower mirror. It's with the laser interferometer, which works essentially as a very much improved version of a speed trap used by the police. To transition to quantum absolute gravimeter, you do something very simple. You take this classical mass, you take this macroscopic object that you normally would drop and measure, and replace it with a bunch of atoms, and then drop them and measure how fast they are falling. So what you measure is the classical motion of the atom. In that sense, those devices are very different from other kinds of quantum sensors, which are usually the measured quantity is something fundamentally quantum. It's something like it's related to their spin or energy levels or stuff like that. That's things, if you're familiar with the terms. There's all sort of, those are things that are fundamentally quantum. Here, we just replace the test mass and just measure how it's falling. So that begs two questions. First, why am I talking about this in a quantum webinar? The answer to that is how. You cannot just aim your interferometer, your speed trap at a bunch of freely falling atoms and expect to get a signal. In order to interrogate, in order to measure how they're falling, you must have you must address those atoms as the quantum creatures that they are, and utilize their quantum properties. The second question is why bother? Wouldn't it be actually simpler to use your normal mirror macroscopic object that you can hold in your hand, rather than this amorphic atom that you somehow are supposed to measure and involve quantum mechanics? So as it turns out, the surprising answer is no, it's not simpler. Actually, such devices will have similar sensitivity, both kinds, quantum and classical, and they will be limited by similar factors, such as vibrations of the environment. And the advantages of the quantum gravimeters are in more mundane, practical reasons. It's much better to have a test mass that you create on demand, and when you drop it, and after you finish interrogating it, it dissipates, rather than having something big object that you need to grab, release, catch, bring up. It's a mechanical system. We have finite mean time between failures. It causes vibrations when the mirror hits the bottom of the apparatus. you avoid all those by using those atomic test masses. And furthermore, beyond gravimetry, this approach gives you more flexible capabilities and allows you to measure more things than what your standard classical gravimeter would be able to measure. So what I'll talk about in this lecture, I will start explaining the principle of operation. How do we measure this gravity with the atoms? Delve a bit into the quantum mechanics, try to give some intuition of what is the quantum mechanics, how does it work, and then I'll just try to cover from the bird's eye view where this technology of gravimeters is around the world, and then I will briefly touch other applications, other realizations of atom interferometers for measuring other things like gravity gradiometry, acceleration, rotation, etc. So, as I said, for the quantum gravimeter, we need two things. We need the test mass and we need the interrogation. I will spend the next several slides explaining about the interrogation, but I'll briefly touch what do we need for our test mass. So, of course, any object on Earth is falling down with a gravitational acceleration of g. Even the molecules in the air in this room do that. However, those molecules are hot. They are room temperature, 300 Kelvin, which means that they are zipping around with typical velocities of hundreds of meters per second, and they're in atmospheric pressure. That means that there are quite a lot of them in each volume. So what that means is that those atoms and molecules in the air constantly hitting each other and the walls of this room. In between such collisions, they undergo parabolic trajectory with g. If I could measure, I would be able to know g. But those sections are very small and unpredictable, and it's not something practical to work. So how do we do? Well, what do we do? How do we get an atomic test mass? So capability that has been developed in the physics world in the last several decades is the ability to laser cool atoms and create such a cloud of very cold atom in a vacuum chamber. So what you get you have those atoms are very cold. Their typical thermal velocities are on the order of millimeters per second or centimeters per second. So that means that if you let them go, they just fall down, and they mostly fall down, and they will hit the floor before they hit any walls. This cloud is fairly dilute, and they move slowly, so they don't hit each other, and it's in a vacuum chamber, so they don't hit anything else. So this makes them a very good test mass. I will not talk about how we achieve that. This is a topic for an entire different lecture. So for the moment, just bear with me and trust me that we can achieve that. We can create such a cloud of cold atoms. We can let it fall, or even throw it upwards in a controlled velocity. Everything is done with lasers and magnetic fields. And we have our desired test mass. Now, to understand the interrogation, I would like to take a step back and talk a bit about some quantum mechanics basics. I assume most people here heard about this and studied it at some point, at some level, maybe previous webinars as well. But since I assume most of you don't deal with that on a daily basis, I thought it would be worthwhile to go over some basics. So let's forget about everything we talked about until now and just think of an atom, a single atom that's floating somewhere in the air, doesn't go anywhere. It's still a fairly complex system. It has a bunch of particles, protons, neutrons, electrons, all attracted to each other, repelled from each other, they're zipping around. All of this can be in many different configurations, different positions, different velocities, all that. So that's a complex problem. But fortunately, what quantum mechanics tell us several things that really simplify how we can address, how we can treat this atom. What quantum mechanics tells us is that you cannot have any possible configuration for all those constituent particles. you have only discrete set of allowed configurations. So I don't know exactly what's going on in this configuration, but I know that it's discrete. And furthermore, I can isolate, you can choose like 1 or 2 or 3 of those allowed configurations and assume that only they matter. Everything that will happen with the atom will only be with those atoms can be described by the atom occupying those levels. So I can label them somehow. So what you see here is labels within those funny brackets. It's just a name. You use it 1, 2, 3. It could be letters. It could be a Mickey Mouse, whatever you want. And so that's an important thing. And okay, what I will say now is not exact, but it's a good enough approximation for the purposes of this lecture. When the atom is in one of those states, it will stay there. If nothing external acting on it, it will remain there for a long enough time period. It's obviously not precise, and there are very important fundamental exceptions to that, but they are not important for the purpose of this talk, so we will ignore it for the time. Another important thing is, I'll skip the other thing. So if we want, another important thing is that we can associate with each level a number. We call it energy. So we also call those states energy levels, or we can treat it as a frequency. It would be better to treat it as a frequency because what this means is that we can couple those different states. We can force the atom to transition from being in configuration state 1 to configuration 2 by applying an electromagnetic field whose frequency is exactly the difference between the frequencies of those two levels. So for levels that are close together, this frequency might be in the microwave regime. For levels that are further apart, this frequency might be optical, laser, you use laser in the optical regime or IR. And of course, everything in between and beyond, those two examples are just the most convenient to work with our human technology. So what happens when we turn on such interaction? What essentially happens is that the atom will continuously go between those two states. This is the place to remind you that another very important principle in quantum mechanics is that the allowed states having some allowed state doesn't mean that you can only be in those allowed states. You can also combine them. So you can be in 1, you can be in 2, but you can also be in a combination of half 1 and half 2. And what happens when you turn on this electromagnetic radiation that will couple 1 and 2 is that slowly and continuously the atom will move from being in a state that it's entirely in 1. It's the part that's the size of the one component of this of its wave function, of the way we describe it, will slowly decrease, and the part that's 2 will slowly increase until they completely swap places. When they completely swap places, we may imagine, we can call it that the atom has absorbed a photon from the field, but we imagine it as something discrete, but in fact, this process is continuous. It's just a certain point in the process, and it continues after it absorbed that photon. We now have the number of 2, the amount of 2 in the wave function decrease, and the amount of 1 start to increase, and until we may return back to the initial point. Now, important thing about this combination, those two components, 1 and 2, they add up as wave. So the best analogy I can think of to someone familiar with classical engineering would be light. Consider 2 orthogonal polarization of light. So 1 can be treated as horizontal, and 2 can be treated as the vertical polarization. And you can have any sum you want between them. So if you are entirely in 1, so it will be just 1, but it can be half and half, and then you'll be either diagonal or circular, depending on the relative phase between them. So this is what we have here. We have something that determines the amplitude, how much we have of one and how much we have of two, and we have a phase between them. The phase will be important, remember it, but we'll drop it for the moment. And of course, what we're showing above is the how much one is essentially the intensity. It's the amplitude squared. So it's again, exactly like with polarized light. If you have two polarization, mixing of some two polarization, and you separate them and measure the intensity, you will measure the square of each of their amplitudes. And we want here to conserve, we have one atom, so let's have a cosine square and sinus square. Never mind what theta is, it will always be one. So this is good, this is fits our intuition. Now, the next thing I need to talk about is now that talk about the atoms falling down. We need to take into account that they are moving, they can have motion, they have velocity, or momentum, velocity and momentum for the purpose of this topic, same. So if the atom, we have an atom starting in one and it has some velocity or some momentum p, when it absorbs, the best way to visualize it is when it absorbs the photon has momentum. Electromagnetic radiation has momentum, it has kind of blood pressure, and this momentum depends on the wavelength, on the wave number rather, and when momentum conservation exists even in quantum mechanics. This one we keep, we don't, it doesn't go anywhere. So when we absorb this photon, in fact, we don't couple exactly 1 to 2, we couple 1 with some momentum to 2 with slightly bigger momentum. So it has a recoil, like a gun when you shoot. It absorbs the photon and it got its momentum, and so it's now moving with slightly different velocity. So and this velocity depends on the wave number, the optical wave number of the electromagnetic wave. So this is very useful and important because that means you can now imagine that our atom is some sort of a wave, and if we now apply a pulse that completely switches the state, we go entirely from 1 and 2. If we look from outside and don't care about what's happening inside, we just see that the atom was entirely with such certain momentum, and then the atom is entirely with a different momentum. So it's like a mirror. We completely change the trajectory of this atom. More interesting is the case where we stop the pulse here and we're in equal mixture, equal superposition of the two states. And then when that happens, it means that half of the atomic wave function continues moving in the original trajectory, but half is deflected to the new trajectory. Essentially, we have a beam splitter. So, and this essentially means that if you perform a beam splitter and wait some time, after some time, the atomic wave function would look something like this image. It will have two parts that are spatially separated by, it can be a macroscopic difference, it can be millimeters or centimeters, which is a huge scale in atomic terms. So the take-home message from the last two slides is this: you can treat atoms, as waves, probably buzzword that you heard before. But the crucial thing is, you can use electromagnetic radiation. You can use light as optical components for those waves. You can use them as mirrors or beam splitters. So now we have everything we need to build an interferometer. Here we have an image of a standard interferometer. It's called the Mach-Zehnder configuration for those not familiar. It has a source for waves, it can be a laser, it can be a lamp, and it has optical components that physicists would usually buy from vendors such as Thorlabs or Edmund Optics. Not sure how it happens in other configuration. And we have here that the laser beam comes, hits a beam splitter, splits into two ways. They are redirected, mixed again on the final beam splitter, and some of the light goes here and some of the light goes there. And from the ratio of how much light went here and how much light went there, we learned something about what happened to the light within this interferometer. The same happened with our atoms. We have a source, our freely falling cold atom cloud, we have optical components which are transition between energy levels. It's actually a bit more complicated than I told you in the previous slide. We use laser beams two laser beams coming from two directions. It's not really important why, and we'll not get into these details, but for all intents and purposes, it can be treated very similar to what I showed in the previous slide. And we can build an interferometer exactly with the same principle. Now, instead of two spatial axes, we have here a time axis. So we have our atoms freely flying through the air. Beam splitter splits them. They reach some macroscopic separation. We perform a mirror pulse to redirect them to each other, mix them with a beam splitter, and measure what happened. Where did the atoms go left or right? And from how many atoms went left or right, we learn something about what happened. What do we learn? What is the phase of the interferometer, which is what determines how many atoms went which way? It turns out that this is determined by this term that I mentioned before and we quickly forgot about the phase between the two parts of the superposition. The important thing about it is that each pulse imprints such a phase, and this phase actually is fairly simple. It's simply a KZ. It's the effective wave vector of our electromagnetic field, of our standing wave light, sort of, multiplied by the position of the atom. So now we apply those pulses when there are four positions, because here there are two arms, and it turns out that when you correctly account for the signs of the different contributions, you get nothing but the second derivative of the height of the z coordinate with respect to time, which is acceleration, or in our case, gravity. In a sense, each of those laser pulses serves as a ruler whose ticks are defined by this wave number or this wavelength determined by the effective wave vector of the two light beams, and it somehow encodes information of the position into the atoms, and eventually transforms this information into information about the acceleration. To put it more quantitative terms, it means that for typical numbers where t is on the order of tens or hundreds of milliseconds, and we have Earth's gravity and we have the wavelength of the lasers that we're using, gravity corresponds to about million radians, give or take an order of magnitude. That means that you can quite easily resolve very small changes in gravity by, here we have on the y-axis essentially possible results for measurements of, for example, how many atoms went into 2 out of the total number of atoms, doesn't really matter. We get as function of the change in gravity, and if we know within which dynamic range we are working, if we roughly know the value of gravity, we can invert and say, okay, if we've got half, that means that we are 80 micro G away from where we expect it to be. So this is it. This is the basic idea of how such devices work. Basically, that covers most of the quantum parts of such devices. Beyond that, a lot of it will be fairly straightforward and fairly common to the classical devices. So from now on, it will be more bird's eye view, a lot of, say, nice pictures of where this technology is in our lab and elsewhere in the world. So as I already said, this is an image of our apparatus in our lab in Rafael that we built in collaboration with the Weizmann Institute. We have, okay, so that's the image we always show, but this is the vacuum chamber within which we create our cloud and interrogate it. But actually, that's just a small part of the entire story. We have behind it an optical table with a lot of lasers and the optical components, and we have several racks of equipment, drivers, supplies, etc., etc. Of course, it's not just this nice apparatus. And this is very much a laboratory-based setup. And so what happens here? So we can show you several typical examples of results. So we create our cloud in this bottom chamber and launch it upwards. There are some numbers here for those interested. And here we have a series of images taken with a CCD camera at different times when we launch the atoms at a relatively slow velocity. And we can see that they undergo the expected parabolic trajectory. And also they have that the cloud is slightly expanding. This is expected at those temperatures. The expansion of the cloud should be about millimeters per second, centimeters per second, and this is exactly what we see. So while the atom undergoes this parabolic trajectory, we perform our laser interrogation. We measure, we can leave this system now running for several days and keep track of the gravity values that we get over that time. And here we see example of such a measurement set of about, as I said, about 3 days long. From 2 years ago, by the way, it's not this December. And we see here that we did some binning, a half-hour binning, and we see that the gravity changes with time, with some periodicity of about 1 day, and with a scale of about 100 nano G. What is this changes? Those are tidal variations. What we feel, when the gravity that we feel here is primarily the gravity of Earth, but we also feel the gravity from the moon and from the sun. And as the Earth rotates around its axis, the direction of the gravitational pull of the moon and sun change, and the total gravity that we feel changes with it, because when they all add up together, we feel more gravity, and when they are in the opposite direction, we feel less gravity, etc. And indeed, the black curve is the expected tidal variation with no fitting parameters up to some vertical offset, which may depend on factors that are known to us. And we see that indeed we follow this curve quite nicely. So there are, of course, more such devices in the world. And one direction this field is taking is building gravimeters for other applications outside the realm of physics, for geophysics, for making a gravimeter, putting it on some mountain and tracking the underground water there, or putting it on a plane and mapping the gravity field in some region. So some devices like this are shown here. This is a device made in a university in Germany. You see here, a bit smaller and more, but still maybe more complicated vacuum apparatus, and all the optics and the electronics that we saw earlier spread around is all focused on those racks. So such device can be brought to some measuring station and be set up for measurement within, I don't remember exactly, I think a couple of days maybe. Another example from the academia as well is this device built in Berkeley, where now everything fits inside this single rack, both the vacuum chamber and the optics and the electronics. And this device, they even took it for a ride in the Berkeley Hills, and they took measurements. They could not perform measurement while driving, but they could stop, take a measurement, and continue on for some time. And this field is already starting to leave the world of academia and enter the commercial world. This sleek device is already a fully commercial quantum gravimeter that does not require physicists to support it. It's supposed to be completely turnkey. You are a geophysicist that doesn't know quantum mechanics and don't care about quantum mechanics. You get this box and you set it up somewhere, and you can measure gravity for however long you want. A few more companies are actually entering this world. I think that, and there was one company which is mostly for defense application in the States that is even older. Another very nice example is by a group another group in France, where their national aerospace lab. They build a device which is also mobile, and they actually perform gravimetric surveys on sea, and mounted this gravimeter on a ship. And here you see the example of their survey compared to the expected measurements that in this case were gotten from satellite measurements. And they even performed these measurements in an airborne survey, mounted it on a plane and flew over Iceland. It's difficult to tell, but this is Iceland. And again, got some really nice results and very nice improvement with other measurements of those regions. Now, this is one direction that this world is taking. Another direction is applying those gravimeters for fundamental science. So those are still the laboratory experiments for physicists, not for geophysicists. And for example, here we have another laboratory experiment, but with a small difference compared to ours, or not so small. This tower is 10 meters high, the ultra-high vacuum apparatus, and they throw the atoms inside there for a few seconds of free flight. This allows them very long interrogation time. Other few devices were built to operate on 0G conditions, so that's already outside the lab. It's difficult to get 0G in a terrestrial lab, so there was the device that built to operate on 0G flights, parabolic flights, a device that was mounted entirely into this capsule and was operated in this drop tower in Bremen. And from the same day later, the next generation, they mounted it as a payload on a sounding rocket and launched it into space and had it about 6 minutes of microgravity while it was falling down. All those are applications for basic research. They are trying to get a very long interrogation time for measurements of equivalence principle. They have two kinds of atoms in each such experiment, and they want to measure what if there is a difference in how fast they're falling, if there's a difference in their gravitational acceleration. So far, they haven't found, surprisingly. Finally, a few words about other applications. So the first application is gravity radiometry. It's, in a sense, it's fairly straightforward. You start with your gravimeter and then get another one on top of it, but not just another vacuum apparatus and duplicate everything, but you actually create two clouds within your vacuum chamber and have them fall at the same velocity, but with parallel trajectories, but separated by some distance, height, and interrogate them with the same pulses. So you will get some measurement for one of them, you will get some measurement from the second, and both of those measurements independently may be noisy, but when you plot them one against the other, you will get a nice Lissachou ellipse. And as it turns out, quite a lot of the noise will be common to both interferometers. It would just move both fringes together. It would essentially move the point on the ellipse. However, we don't care where we are on the ellipse, because if we want the gradient, if we want the difference between G2 and G1, it is only determined by how eccentric the ellipse is, only by its shape. So that means that you reject quite a lot of your noise, which is compared to regular gravimeters, which is makes it quite powerful. Such devices are less mature, but there are still some examples that are already slowly starting to pop up and show some performance, at least openly. And practically, in terms of numbers, the demonstrated performance is comparable with state-of-the-art classic devices. Not quite there yet, but getting there. Another thing is accelerometry. So in a sense, okay, so gravity and acceleration, we all know that should behave pretty much the same. It's not supposed to be much difference. But there are some small differences in realization. The first one is that you know which way gravity points downwards. You can make your entire system one-dimensional. The atoms are falling, lasers are coming from the top, everything is one-dimensional. For accelerometer that you will probably want to mount on a navigating platform, your direction will be random. You cannot rely on it being in a certain direction. You need to measure in all three axes, and you still have gravity, which means that you cannot have very long interrogation time, because the atoms will, if if you are trying to measure in a horizontal axis, your atoms will just fall out of your laser beam. So that leads to devices that are more compact size. At the moment, such devices are still in very early laboratory stages. Not familiar with anybody who took one out for a ride outside, like the gravimeters. And there's another difference in terms of what exactly you want, how exactly your data should look like in terms of what is the bandwidth of the desired information, something that I will not go into unless somebody would ask that in the questions. And finally, I will mention, of course, inertial sensing is not full without the ability to measure rotation, to have a gyro. So there are several ways to explain, to give intuition of how exactly an atom interferometer measures rotation, and they're pretty much equivalent. The simplest and the most probably universally understood one would be if the system is rotating, there is a Coriolis acceleration. So the atoms are freely falling, but if now the lasers are rotating, and now you measure in the system of the laser, so the lasers see as if the atoms have Coriolis acceleration. And this acceleration, and we can measure it, so problem solved. Well, it's not so simple, because if you're rotating, you might also be accelerating. And what separates it from the contribution of the Coriolis acceleration from the regular acceleration? Not much. In a single interferometer, you will simply have a known combination of the two, so you need to separate it somehow. So there are several schemes to do this. One example is what I'm showing here on the right. You create two clouds and launch them toward each other with opposite velocities, and interrogate them at the same time. So both clouds would feel the same acceleration, because this does not depend on their velocity, but the Coriolis acceleration does depend on the relation between the rotation and velocity. So they will feel opposite Coriolis acceleration, and if you measure both of them, you can get out the required information. In fact, this specific scheme, they demonstrated the 6-axis measurements by using 2 clouds and 3 interrogation direction. Now, there are other schemes for atom interferometers, essentially rejecting the contribution of acceleration, gravity, or just spurious acceleration from the rotation signal. To be honest, they are not really competitive quite yet. So if you are building ring laser gyros, you are not in danger to go bankrupt any soon because of that. But a lot of work is being spent in that direction, and might have something interesting in a few years. And the other thing, important thing that I want to mention, is that this is not the only kind of quantum gyroscope. There are other kinds of quantum gyros that are not atom interferometers, that do not rely on the classical motion, but on other effects. And this is a whole different lecture, but just be aware that I haven't covered all possible. So in the 1 minute I have left, I will try to give some context of what we are doing in our lab. We're obviously not taking our device out of the lab to measure the underground water on some volcano, and we're also don't fly it put it on a rocket. So what we are trying to do is to develop in our lab in Rafael. One of the things we're trying to do is to develop schemes for better, for more robust operation of such devices, such atom interferometers. So, for example, one of the problems fundamental problems of such an interferometer is the dynamic range. It is fundamentally limited by 2 pi. So, if you know that you are between here and here, and you make a measurement, you can tell where you are. But if you don't, if you are not sure if you are here or here, you cannot tell the difference between those 2 solutions. So a typical solution would be to change the parameters of your interrogation to increase the dynamic range, but this generally hurts sensitivity. What we did is we applied that scheme where we took advantage of from small changes in the interferometric sequence to acquire a high dynamic range while keeping the high sensitivity. without going into too much details, this is example of a measurement with a certain G value. This is example of a measurement with similar G value that's slightly different that we would be able to resolve even with standard interferometry. And this is example with measurement with very different G value, which we would probably be with standard interferometry completely overlap with either this or this fringe, and we will not be able to tell the difference, but with our scheme, we quite obviously can. So bottom line, without going into details, we demonstrated orders of magnitude gain in dynamic range without hurting sensitivity and without hurting bandwidth, even within a single shot. So with that, I finish. The precise and accurate measurements of the motion of freely falling atoms relative to the lab or platform, this is what atom interferometers allow. This is what you get from them, and this means that you can get information about their motion. For a terrestrial stationary lab, it would be gravity, maybe Earth rotation if you are sensitive enough. For a moving platform, it will be the acceleration and rotation of the platform. The atoms serve as flexible and convenient test masses. They are actually more convenient to work with than mechanical and microscopic objects. And it is a maturing technology pursued by many companies, even already commercially available in the case of gravimeters. So thank you for your attention. Our group essentially is a collaboration with Rafael and Weizmann Institute of Science. Those are the participating people. And thank you.
Dr. Yankelev, thank you very much. Ladies and gentlemen, this is a time for your questions, so please don't hesitate. Don't be shy. Do you think that the potential for gyros in the future, I'm not talking about this time, but let's say 5 years from now, it may provide better and better accuracy for gyros?
There is room for improvement. Existing technologies really set a really high and challenging bar, but it's quite possible.
Okay. And it will be more robustness than the others, the classical gyros?
It's quite difficult to answer that. So in all likelihood, such devices would serve not as a standalone measurement units, but for something that would work in tandem with the other classical gyro, in order to give it to help stabilize it in the long term. So as I said in the beginning, so that it is generally true what I said in the beginning for the comparison between relative and absolute gravimeters. It is also by coincidence generally true for classical sensors and quantum sensors. Classical sensors usually allow very high sensitivity but bad stability, and quantum sensors are usually somewhat the other way around, and combining the two allows you to enjoy the best of both worlds. So with gyros it will probably be the same. Good enough atomic gyros would serve as a reference to stabilize possible drifts in the classical gyros. So that doesn't exactly answer your question, but they will have to be of similar robustness for it to be useful.
What about miniaturization? So taking it and to the level of chips like photonic integrated circuits? Okay, there are quite a few challenges there. In the practical miniaturization direction would hope for not a chip scale, but for something this big. For compared to what you saw for about a meter high or half a meter high or
30 centimeters high devices that exist today. So the possible direction for miniaturization are likely to go in the centimeter scale, or I don't know, up to 1 liter, say, or a tenth of a liter. So this is a relevant direction. Specifically, there is a possible idea for chip scale gyro, where the atoms are traveling in a circle and are interrogated with the atom interferometer sequence. This technology is even less mature and even more into the future, but if it will come around, it will be possible to miniaturize.
Right, very interesting. Thank you very much. And I would like to wish you a good success in the future.
Thank you very much.
Okay, thank you all. And good night.
Good night.